3.
In this case, we placed the centrifugal pump at the reservoir at the bottom, and we're using the pump to force water through this discharge and back into the top. If you're looking at the pump, this is the inlet and this is the discharge, or the intake and the discharge. And if you look at the dials, you'll see that at the inlet to the pump, the pressure is relatively low. In fact, it's reading about 0, whereas at the outlet it's reading about 100. So the pump is delivering pressure head to the fluid, and that pressure head is then able to be converted to extra elevation head. The thing to note is that at the entrance to the pump, I have the hose on there without a clamp. Hopefully the answer or the reason for that should be obvious, because the pressure there is so low, there's no chance of leaking, there's no chance of bursting, or the pipe or the tube being forced out. However, at the discharge end, I'm needing to have a clamp and tighten quite closely, because if I was to loosen that clamp, I would get an early shower. Okay, so the operation of the pump, providing extra head, extra pressure at the inlet compared to the outlet. Now, coming from the reservoir, the water's having to come through this gate valve. The gate valve can be adjusted to adjust the flow or intake to the pump. And as we know from theory so far, that the gate valve has a different resistance factor as the tortuous path for the water to get through it. If it has to move through a very tortuous path, there's more resistance, so the K factor for a semi-closed valve will be a lot higher than one where the water can flow through without much of a tortuous path. So in this case, the valve is open, and now what I'm going to do, I'm going to start closing it. When I start closing it, what's going to happen, of course, is the K factor for this is going to increase. And as we learnt this morning in class, as the K factor increases, the head at the intake drops progressively lower. And as it drops progressively lower, if I can drop it to a level where the pressure that this water is feeling is below the saturation vapor pressure, even at 20 degrees, the water is going to boil, and as you can see, the bubbles are starting to form. So we now, and you notice the pressure so low that the actual tube is starting to squash inwards. And lo and behold, not only are we seeing the bubbles of air, which is really steam at 20 degrees, we'll just turn it up for a minute, but that noise that you're hearing were the bubbles entering the pump, and when it comes to the high pressure end of the pump, the bubbles collapsing inwards, which we call imploding, and that collapsing inwards creates huge stresses on the blades or the impellers that can eat away the impeller very, very quickly. This is what we call cavitation. So the saturation vapor pressure being reached by increasing the K factor, so the pressure is so low now, it's probably dropped to about 2 kPa absolute. Remember, it's absolute pressure now, and the water is actually boiling, and you can see all the bubbles of steam, which is cold steam. It's 20 degree steam, and you can hear the noise. And if I leave it on long enough, I'll have to change my pump, because the impeller will have huge holes in it. Okay, so this is a demonstration of cavitation and saturation vapor pressure. So I hope it was fun and at least educational.